And I believe I forgot to post the video from last lecture, so I'm going to do it as soon as possible. There was some issue with my Dropbox last week when I got a request to post the annotated slides. I just sorted it out. So I should have a copy now. So today we're going to continue on talking about branches by first going to recap as usual. One thing I want to correct myself about the case where you have wrong prediction. Earlier on, I said it's only one cycle. Actually, I make that mistake. It's actually more than one cycle if you do a incorrect prediction. So over here, your first instruction, fetch, decode, execute, memory, and write back. This is normal, right? Like usual. You make prediction. You say, hey, let's take that branch. You are going to fetch. You are going to decode, execute, and then at cycle number 3, what happened is the execute knows that, hey, it's a branch. And that's the what's the result of my branch? Over here, branch not equal to, right? So you start at cycle 3. In the earlier example, what I said is like, okay, we can resume. Basically, we get rid of the instruction 2. Resume in cycle 3. The problem is actually you can't resume in cycle 3. You need to get rid of this, right? And you need to start fetching from here. Oh, not here. Here, cycle number 4. Instead of starting at cycle number 2, you know the result in the execute stage, which means that the next cycle you can fetch the correct instruction. So you fetch, decode, execute, memory, and write back. Over here, cycle 2 and 3 for instruction 2, right? Instruction 2 becomes bubble and bubble. Both of them are empty. So the overhead is actually 2 cycles, not 1 cycle. So my bad about that. Here, hopefully you got the correct idea now. Then we talk about what information do we need if you need to figure out if it's a branch. So the first thing you need to figure out is if the instruction is a branch. The second thing is, okay, if it's a branch, do we take the branch or we not take the branch due to PC +4 or target? If we do target, what is the target address, right? So there are 3 things you need to guess, essentially. 3 things that you need to guess. The first thing is the simplest one to guess. Figure out if the instruction is a branch or not, because the observation is you don't modify your own code when you start to run your program. So if you look at PC, let's say address 0x04, and that's a branch before, the next time your PC is at 0x04, it's probably branch instruction again, right? PC value of branch will stay the same. So you can use that to figure out is this instruction a branch or not. The next thing next easiest thing to guess is, okay, if this is a branch, where do I jump to, right? So that's called the target address. Usually when you have these prediction, most branches jump to the same target address. Why is that the case? If you have if else, right? These first lines are the same, right? The first line of the if and the first line of the else are the same PC. So most of the time when you jump to the same address. So we can store the possible target in the large buffer, which we call the branch target buffer. This looks like a cache for branch target address, right? Record the previous time when you have to branch what's my target. And based on the PC value, this branch target buffer would give you a target. So here's the structure of the BTB. So you have the branch target buffer right here, right? This is your target. Oops, same color, so you can't exactly see what I wrote here. So I'm going to use a different color. Target direction, right? If you can find the target, it means that, okay, I run into this branch before, so I know where I'm jumping to. If it's taken, then you jump to your target. If otherwise, you do PC +4 to the next instruction for the next PC. So here is the overview we know so far. And we talked a little bit last lecture about the branch direction, right? How do you determine that? And in particular, these are the things that we talk about, right? When you look at the branch during the runtime information, you can use multiple techniques. Last time prediction using a single bit. If I take the branch last time I see this PC, I'm gonna take the same branch. If I don't take the branch, I'm gonna also not take the branch. Here's the state of the last time predictor. There are two states: predict not taken and predict taken. If you predict taken earlier, basically you say, hey, I want to predict that I'm going to take this branch if I'm in this if else, I'm going to go to the else part, right? And then you actually go into the if part, which is not taken. Then you go to the predict not taken because the last time, basically this time you are not taking the branch. So you think that the next time you see this if else again, you are not going to take the branch. Otherwise, you stay at the same state, as you can see here in the state diagram. So this thing is called state diagram. You have a state of, okay, currently we're going to predict not taken. Currently, we're going to predict taken. If this happened in reality, are we moving from one state to another? This is why we call it state diagram. So let's look at the state diagram of 2-bit predictor, which is what we covered last lecture as well. So it's 2 bits. You can have 2 states for predict taken. One of them is a strongly predict taken, the other one is weakly taken. Then the 2 more bits for not taken part. The difference here is if you're strongly taken, and in reality, you take the branch, you stay at the strongly taken because you've seen a lot of taken branch already. So you can stay at the same place. Otherwise, you are moving from 0, 0 to 0, 1 because you want to predict that, hey, you should take this branch. But in reality, you're not taking the branch. So you lose confidence. I'm like, okay, I guessed wrong this time. So maybe in the future it's not taken. So you move from 0, 0 to 0, 1. I'm still going to predict that I'm going to take that branch, but I am not as confident as before. If you are at the predict not taken and you take the branch, you're more confident. So you're going to move back to the strongly taken path. And this is for the bouncing between predict taken and predict not taken. If you're not sure if you can predict taken or not, and the result go into another direction that you predict, then you move to a different state as I show here. And here's the rest of the state where if you are in the weakly not taken, and in reality you take the branch, you go back to the predict taken. Otherwise you predict correctly, so you go to a strongly not taken. You're more confident that you want to take the branch. So because the control flow is frequent, so for those of you who did the in-class exercise, how many if, else, or loop did you count that ended up on your assembly code? What's the fraction of the jump or branch instruction that you see? Anyone did the in-class exercise from last week? You got 2 out of how many? 90. Okay, the compiler is doing a really good job, so that's good. There were papers that report a number between the 5 to 10% of your code jump or branch. This is a friendly, like hardware friendly code. If you only got to 90, basically, if you have if, else, or loop or function calls, essentially, your fetch address is not determined after n cycle. So if we fetch m instruction per cycle, basically, if you do what we call superscalar, so you forgot what superscalar is, go back, I think, 2 lectures when we talk about pipelining. Superscalar means that instead of fetching 1 instruction at a time, I'm going to fetch m instruction, which is what your CPU nowadays do. In the GPU, you even fetch more. You fetch way more instruction per cycle. So when you have missed prediction, this is going to be n multiplied by m wasted. right? Wasted instruction slot. We did a rough calculation from the last lecture. So over here, if it's, let's say 2090, that's around 2% of your code are branches, then I can say that if you are doing really bad job at predicting the outcome of your branch, your program can end up being about like I would say 3 to 5% slower, right? For that particular exact code. Okay, so what happened is your main body of the function, I think when you do Fibonacci, is basically the add ones, and you have a setup code when you load the data, right? And you have the setup code at the end when you return to the main function and finish. So the actual like loop body, you have two branches and then maybe like tens of line of code that is not the setup ones. So when you look at it, you're looking at roughly at maybe 5% of the code that you run each line, right? Those are branches. And then when you branch, you also need to kind of factor in the part that your code is 90 lines, but the if part is 10 lines, the else part is another 10 lines. When you run, you only run 10 of those, not 20. All right, so hopefully, I mean, in class exercise doesn't really stress out the importance of branch. I'm sorry about that. I thought it'd be more with Fibonacci because it's branch in two function calls essentially. But we can actually do things in hardware to make it such as most of the brands are going to guess correctly. With modern day branch predictor, anyone want to take a guess actually at what percentage of branch that we can predict? So you read like architecture paper in the last, so the last major branch prediction paper was about 2004, so about 15 years ago. The one that I told you that this is used in Samsung mobile phone. So in that paper, anyone want to take a guess how many percentage of misprediction that you see in the program? So the 10% one is actually way back in probably 80, 85, 90s. With that work, you're looking at roughly between probably 1 to 2%. Like maybe 1.5% actually. Only that. The rest you can guess what you go, where you go. That particular technique used perceptron, which is part of like machine learning. So it try to learn the pattern you see and then adapt to the program you run. But anyone here use Docker or Cloud to run your program? Yeah. Okay. So have you realized whenever you use Docker or Cloud, it's a little bit slower than running on your machine? Even though, I mean, okay, for each task that you run, it's going to be a little bit slower. Part of it is the overhead where you need to convert the things like namespace. You have the OS overhead. When you go to virtual memory part, I'm gonna tell you what's wrong with virtual memory when you have to run things like virtual machine and why that can be really slow. So hopefully you're looking forward to that. But the other thing that Docker kills is branch predictor. The problem with that is, what do you do in Docker? You call a function, right? You just call a function and run it using Docker. Only one function. And then someone else can run a different function, right? If you look at the techniques that we are going to cover today, right? Anything from this slide onward, you notice that if you're going to have multiple function calls coming from multiple programs, it destroys all the history that you see. So branch prediction performance tanked. Actually, there was a paper from, I think, 2018. So 2 years ago, I was about to say last year. There was 2018 that look at the branch prediction performance with Docker, with like function as a service, basically those cloud service. And the paper showed that, okay, this is really bad. You need to now come back and think about how we solve this problem again. So hopefully this is, I know it's sidetracked, but I find this exciting because no one worked on branch prediction since like 2005. And then because it's really good, like it's good get to like about 1% inaccuracy. And then suddenly when you have cloud, what input do you put into perceptron? The basically things like PC, depending on what you want to do, basically you will try to learn, right? So things like program counter, the outcome of the branch, those are feed into the perceptron, you adjust the weight, and that weight becomes, basically not become, but it try to learn the pattern from what you see. Think about it this way. When you are building the perceptron in the hardware over here, you only have the fetch and the decode information, right? Because branch predictor is this what somehow we call this front end. Front end is this, which is not the front end that you are used to, not the front end on the web interface. The front end of our pipeline, fetch and decode. Somehow we call the memory part back end, memory and write back. The front end part are branch, instruction fetch. So those are the information you see. Input into the perceptron, learn from whatever information you can gather at the front end, basically. So hopefully, does it answer your question, basically? Okay, yeah, so these are history that you try to learn and adapt, right? But when you use cloud, the problem with cloud and Docker, you run a totally different application on the CPU. Right? Each time you have a function call, it's a different program by a different user. Think of it this way. I have CPU 0, right? Or CPU 1, let's say CPU 1. I'm gonna start counting from 1. I have CPU 1 on my local machine and I only play Dota. So I'm just running games, right? And it's the same game. So whenever I see the branch, it has pattern. If I click here, I'm gonna walk here. If I click here, I'm gonna walk here. If I click on over that part, I'm gonna die because someone else is gonna kill me. Think about it this way, if you run things in the cloud, at one point of time, you're running Dota. At a different point of time, someone is trying to finish the homework and run the assignment. And then at the next second, you're back to Dota again. The fact that you're switching between two totally different programs kills off all the history you're trying to collect. So the hardware becomes jelly. Basically, it's like become ineffective at predicting things, at dealing with the caching, for example. All right, so I'm gonna come back to our topic. Sorry, we're getting super sidetracked here. And if you want to look into those areas, let me know. I'm working with a bunch of people right now in Zurich to try to improve the performance of containers, basically. If you look at branch prediction, one thing that common, this is like a textbook on branch prediction. We'll call this two-level prediction, and we'll go into detail on how we can go much better than using a 2-bit counter into two-level prediction. So the question we want to answer is, how do we improve the performance of the branch, right? Further, the branch prediction. The first one is, if you look at the branch outcome, right? Something like this. You have a for loop. Right? Inside the for loop, you have if else. This is branch number 1. This is branch number 2. Right? In this case, the way you write the program, whatever is the outcome of branch number 2 would impact the outcome of branch number 1, right? And this is especially true if I do this. If I say that's if else, right? And then now you have branch number 3, branch number 4. And as you can see here, there's definitely correlation between branch 2, 3, and 4. Right? If you go into branch number 2, it means that you don't go into branch 3 and 4. If you go into branch number 3, it means that you don't go into branch 2 and 4. You got the idea, right? Each branch, the outcome of each branch impact the outcome of the rest of your code or the branches. We call this global branch correlation. And for the interest of space, I'm going to erase this part because it's overwrite my text. If you look at each individual branch, the path outcome impact the outcome of the same branch. Do you buy into these two ideas? If you don't buy it, please let me know why you think this might be wrong, because you might come up with a new paper. Because most paper based on these two observations. So do you understand both observations? Basically, there are correlation between different if else or for loop that you write in the code, and there's also correlation into the first time you see this if else, what's the outcome of that, and the next time you see that if else. So let's look at a simple code about branch correlation. The first one that I say, okay, if I look at your entire program, this code, if condition 1 is true, what happened to the second if? If condition 1 is true, what happened to the second if? It's false. So you don't do that something, right? There's a correlation between the first and the second if. The second branch is going to be not taken if the first branch is taken. Yeah, I see this mistake on my slide. This is the third time I see this on the slide and I haven't fixed it yet. Sorry. If the first branch is taken, it becomes 10. So you're not taking the second branch. So how do we detect this, right? On top of tracking the outcome of each individual branches, you can do something like, okay, I want to look at the history of all the branch, right? And there was a paper that actually proposed this idea. The idea called for another register. The register just look at the history of every branches. Look at the past, say, 32 branches or the past 16 branches and look at the outcome. And the prediction is made based on the outcome of the same history pattern, the GHR. GHR is used as the index into our pattern history table. We are going to go into the example, so don't worry too much. This is basically called combining branch predictor. Is proposed in 1993. And here is a brief overview of what it does. This is our global history table. And let's say this is only 2-bit. Let's say this is only 2-bit, which might not be true. In most cases, this is 32 bits. It's actually much longer. If GHR is 2-bit, it corresponds to the last 2 branches that I see. This means that I'm going to look at the last. So if it's n-bit, it means I'm going to look at the last n branches. If this becomes just 2, if this is just 2 bits, let's say it is 0, 0, 0, 1, 1, 0, and 1, 1. If that 2 bits are 0, 1, it looks into this pattern history table. What it does is basically, let's assume that 0 is not taken and 1 is taken, right? 0 ones means that the last two branch is not taken. The last branch that I see is taken. Basically, the pattern you see is not taken, followed by taken. I'm going to look into this corresponding direction predictor right here. That tells me the prediction of the last pattern that I see not taken, taken. If the PHT say, okay, I'm going to predict taking the branch, then you take the branch and get the target address. If it's not taken, you get the PC plus 4 as your next PC. So don't worry too much. We are going through the more detailed example. So hopefully that would give you a more look into how this works. Here's how you implement it in hardware. Here's the example. So let's look at this code. I'm going to have two examples. This example is your in-class exercise toward the end of this class. And this is our example. So for our example, how many branches that you're dealing with? How many branches in total? In example 1. 3, yes. First branch, second branch, and the third branch. Everyone got while there are 3 branches, right? The first loop, you have I is less than 5. The second branch is check if I is less than 3. And the third branch is I is less than 2. Let's assume we have a 2-bit GHR and we use a 2-bit saturation counter for each GHR entry. This is what I'm gonna do next. I'm gonna show the table. Here is the GHR, right? So this GHR, I'm gonna go back 2 slides, I'm sorry. This corresponds to this GHR. So that's the GHR. This is our pattern history table that corresponds to each GHR entry. Over here on the top, I just want to say these are the actual branch pattern. So let's look at the branch pattern. If we look at these 3 branches, what's the first outcome? Let's assume that if whatever is in the if else becomes true, we take the branch. If it's true, we take the branch. So what's the outcome of the example 1? What's the outcome of the first branch? Is it taken or not taken? You take the branch or you not take the branch? For the first for loop, if we assume that if I is less than 5 is true, we take the branch. Yeah. Does yes with the question mark means taken? Yes, we take the branch. So you go into this, right? It's true. So you take the branch, followed by is I less than 3. Well, what's the outcome of the second branch? Also true, right? Third branch is true. Now I is 1. You take the loop. You take the first if. You take the second if. I is 2. You take the loop. You take the first if. You not take the second if because now I is 2. I becomes 3. Take the loop. Not take the first if. Not take the second if. I becomes 4. Take the loop. Not take. And I become 5. You not take the loop. That's our pattern. T T T T T T T T N. Right? So we see taken, 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 not taken, taken, not taken, not taken, taken, taken. So that's our pattern. Same here. Right? Exact same pattern here. So if you run that code, that's the pattern that you see. Can someone give me some initial value? It can be any values, 2 bits for DHR. 0, 0. Okay. How about this local counter, so 2 bits. Okay, I'll check 1 1 for the 0 0. What about the other, the next one, 0 1? It can be any 2 bits. As I said, just give me some initial value. 0 1. Okay. One, 2 more. 1 0. 1 more. 0 0. Okay, perfect. I like how each time I go through this slide, it's always different. So this is what we would do. Let's put in our prediction right here in the table. Right. So what would be, so I'm going to do the first prediction. The way I predict is this. I first look at the, so I'm going to use a different color to see my logic. I first look at the GHR value. So what's the GHR value? 0 0. Right? 0 0. So I look at this and okay, 0 0. So I'm going to look at this entry that corresponds to the same value as my GHR. And let's assume that 0 is not taken and 1 is taken, right? What's the value on the local counter that corresponds to my current GHR entry? What's the value of my local counter? 1 1. If it's 1 1, it means we are predicting what? If 0 is not taken, 1 is taken. If it's 1 1, are we predicting not taken or taken? This is in a strongly taken, so we are taking the branch, right? So our prediction, the first one is taken. Then we are done with predicting the next step. The next step is how do we update this, right? How do we update the branch, all the tables? The first thing that we need to update is, okay, we look at this pattern the last time we look at GHR 0 0, right? So it means that I'm going to look at a local counter. If I'm at strongly taken and my prediction is taken, the actual outcome over here is taken. We are guessing correctly. So how do we modify the local counter? Because we are already at strongly taken and we predict correctly, it stays at 1 1. It stays at 1 1 because we make the correct prediction. It is going to go toward taken direction. It's already at the maximum value. So we keep it there. The next thing we need to update is GHR. It used to be 0 0. It used to be 0 0, which means that the last 2 branches are not taken and not taken. What's the outcome of my last 2 branches now? It used to be 0 0. Now we are not taken and taken. Basically, the way you update this is 0 0, you shift everything to the left, right? One of 0 is gone. Then you look at the outcome is taken, so you put it in 1. Right now, here is your GHR. That's how you update it. So it's 0 1. Any questions about why it's 0 1? Yeah, sorry, I saw the answer 1 1. So I want to make sure that's clear that you basically shift everything to the left, everything that fall out, kick them out. Then you append from the right, or from the right side, the direction that you just took. What we did earlier is taken, so you put in 1. So 0 0 shift to the left becomes 0 1. Basically 0 1. Is that clear? All right, so we are done with the first prediction. What's our second prediction? Are we predicting taken or not taken? Can someone tell me? And tell me why. So the step says, yes, we are at weekly not taken. So if you're at weekly not taken, are we predicting not taken or are we predicting taken? You are correct that we are at the weekly not taken. So our prediction should be what? Yes, it should be not taken. So we are right here, right? Because THR 01, you look at the 01 table, local counter is 01, is weekly not taken. Even when we are weekly not taken, we still think that, hey, maybe it's not taken. So we're going to predict not taken. How do we update this? If you're at weekly not taken, and in reality it's taken, so we are at weekly taken or are we at strongly not taken? Is this weekly taken? So you are changing 01 to 10. How do we update the GHR from 01 to what value? 01 to what? You shift to the left, that become 1, right? The 1 is there. What do I fill it in with? Because we just took the branch. It's 1, 1, right? Yep, exactly. So what do I predict now? If my GHR is 1, 1, wait, right here, right? It's 0, 0, that's strongly not taken. So we are predicting not taken. All right. So how do we update this? Because we predict wrong again. So how do we update this? From 0, 0, we are going to 0, 1, right? Because we're going to be less strong about it. GHR stay at 1, 1 because, well, go back. GHR stays at 1, 1. Why is that the case? We shift everything to the left, 1, 1, and we fill in the taken part, and we take this, so it's still 1, 1. Okay, so with this, what are we predicting next? We add 1, 1. We look at this. It's not taken, right? It's still weekly not taken. So we are still going to keep predicting not taken. Then we update. We update this to 1, 0, right? And then update the GHR. GHR is 1, 1. We take a branch again. Right? We are at, so we are done with this one. We are done with this one. We are done with this one. We are doing the next one. Over here, what's our prediction? What's our prediction for the fifth branch? Taken, right? Because we are looking at this entry and it is now weekly taken. So we think, hey, we see taken twice now. We hopefully would be taking the branch again. So what do we update? We update this entry, update that to 1, 1 because we see so many taking branch. GHR stay the same because we shift one to the left, put in taken again. We finish, we're done with this branch. The next one again is going to be taken, right? We already at max here, we don't update. This GHR stay the same. Done with this branch. We add this next one, taken again. Done with this stay the same again, this stay the same again. This one, taken. Done with this stay the same. Now that we are at the 1, 2, 3, 4, 5, 6, 7, 8, the ninth branch. So let me erase this part. PHT. This PHT. So for the next one, what do we predict? We are at 1, 1, right? For the THR. So we are still going to predict taken because we have seen so many takens, and in all likelihood we thought that hey, it's going to take the branch again, but in fact that's not the case. So what do we do here? From the local counter, we are actually not taking that branch. This gets decrement to 1 0. This becomes 1 0. So what's our next prediction? We are done with here. So what's our next prediction? Yes, it's still taken because GHR is this value. So it goes to here. You look at 1 0. So yeah, it's taken. In reality, it's still taken, right? So this changed to 1 1. This changed to 1 1. Right? So I'm gonna erase and update the table. That's 1 1, and this is supposed to be 1 1. And we're done with this particular taken. Right? So about this branch, not taken. We are predicting taken again because GHR is 1 1. We look at this and like, oh, okay, so strongly, not strongly taken, weakly taken. So we're still predicting taken. We update this table. This becomes 0 1, not taken again. So this becomes 1 0. We are done with that first not taken, right? The next time we see this branch, what's the prediction? Taken, right? 1 0 here. You look at this entry, 1 1, yay. In reality, it's not taken because it's this one right here. So you update this to 1 0. This is not taken 2 times in a row. So this is 0 0. So what's our next prediction? What's our next prediction? Taken, right? Because we are at 0 0. We go here, that take the branch. In reality, it's taken. So you don't update this. It's already at max 1 1. 0 0 becomes what? 0 0 becomes what? 0 1. Yes. And what's my next prediction? Not taken, right? So we're gonna continue on here. My next prediction is not taken because it's 0 1 here. I'm gonna look at this entry. That's 1 0. It's weakly not taken. In reality, it's also not taken. So I'm gonna update this into 1 1, right? And over here from 0 1, I'm gonna change it to 1 0. 1 0, right? Then with 1 0 here, what's my next prediction? It's actually not taken because we are right here. We look at, no, it's actually taken. Yeah, my bad. So you're right. I'm taken because it's 1 0. But in reality, it's not taken. So it's actually changed to 0 1. Then the next one is this entry of GHR becomes 0 0. Not taken, not taken. We are right there. The last branch, not what do we predict? This is the last branch. Taken, but in reality, it's not taken. So, how many times we predict incorrectly? This is incorrect, this is incorrect, this is incorrect, right? And then there's a 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. This is not correct. Taken, this is correct. This is not correct. This is not correct. This is correct. This is correct. Not correct. Not correct. So 1, 2, 3, 4, 5, 6, 7, 8. 8 out of 16. This is 16. Yeah, 16. So this is actually about 50%, which is still bad. But the key here is if this loop run for long enough, if this loop run for long enough, this 50% goes way up to 90, about I think about 93, 95%, depending on how long we are running loop for. Do you want to guess why we are actually getting only 50%? What are the main culprits of this? Why are we doing really poorly here? First about number of bits. Second about the initial value, right? Whenever we see the new pattern in GHR, you look at the value that you haven't learned about history yet. You haven't used the previous information to update it, right? So what I can say is you're not building, you're not warming up to the current loop, current code that you're running yet. So it's going to be wild guess for a lot of time until you set up this local counter to reflect what actually happened. The history become important. So you need to take time to build up the history, right? For most of your program, anyone wants to take a guess how many instructions you are actually executing for a normal legit program? Don't I'm not talking about your Fibonacci function, but let's say a merge sort or something longer. Let's say you have to do a merge sort on 1 million different things. In most cases, you actually look at millions of instructions. If you look at millions of instructions and assume that 2% of your code are branches or 5% of your code are branches, you're looking at about 50,000 branches that you have to do, right? Which means that you're going to take time in the first 100 branches to understand your code, to understand the pattern. And after that 500 or 1,000 branches, it would learn your pattern and it would adapt to the pattern. So obviously, as Cham said, the number of bits are important. The longer you have, the more information you can gather, right? So that's the first, actually, that's one of the most crucial thing that tells performance of this particular predictor. The second thing is how long is your application? So as you increase the length of your program, this particular predictor would get better and better and better. All right, so this is a worksheet for your second part, for the second example. This is part of your in-class exercise. It's actually easier than the earlier example because there's only 2 branches. So I will leave this to you. You can tell me what's your assumption about initial condition. Actually, for this, let's assume everything is initialized to all 0. To make sure all your, you can cross-check the answer with your friends. Everything is initialized to 0. You go through the pattern and tell me what's the outcome of your prediction and what's the reality, like what's the branch pattern. All right, any question about the global branch correlation before we go into the different idea about local branch correlation? Okay. So we're done with the first observation. Let's actually build something that take into account of the history of the same branch. We call this a local branch correlation. And the way we do this is we want to associate the outcome of the branch with the history of that particular branch, right? This is one of the most influential paper on branch prediction is presented in Micro 1991. It's called Two-Level Adaptive Training Branch Prediction. This is proposed by Ye and Pat. The key idea is instead of a global history register, we change it to the local history register that have a set of per PC, per program counter, right? Per program counter that index into a history table. And the second level is just a saturating counter for each history entry. So the second level is the same as the last time. The first level, instead of GHR, we have this big table called LHR. This is a table now instead of one global history register. You then use the program counter. Use it first to index into the LHR. You use the program counter to look into LHR. This will then index to the second level. The rest are the same. The rest are the same. So let's go through an example. Using the same program, branch number 1, branch number 2, branch number 3. So this is going to be PC1, program counter 2, and this is program counter 3. Everyone got the idea that these 3 branches are going to have 3 different program counters, right? It's the line of code on your assembly, and it should be the exact same PC for each branch. So here is the second one over here. This is your in-class exercise. And let's assume 4 entry for the local history register. You have 4 entry, and then we use 2-bit saturation counter. What's the pattern of the first branch? What's the pattern of my first branch? If I just look at that branch, it's just that loop. When I0 is taken, I1 is taken, not taken, right? What's the outcome of my second branch? What's the outcome of PC2? TTTNN. And for the third branch, it's going to be TTNNN. Right? I'm going to copy that answer over to here. All right. Okay, so as you can see here, the second level have a bunch of counter nouns. The second level have a bunch of counter nouns. This is the first level. And as I said, there are 4 entries, so that's definitely enough for 3 branches. And these are the second level. And for the sake of sanity, let me initialize everything to, okay, do you want all zeros or all ones? Pick one of them. Do you want the initial value to be all 0 or all ones? All ones, okay. We have 1, 1, 1, 1, 1, 1, 1, 1. Oh, that's 1 too many ones. All right, so what's my first prediction? Let me tell you how do I get the first prediction. What's the first branch that I see? This branch, right? It's the one that goes into the loop. It corresponds to this branch. So I'm going to look at 1, 1. I'm going to look at this particular table, and I'm going to look at 1, 1. If I see 1, 1, not taken is 0, taken is 1, what do I predict? Taken, yes. So the first prediction is taken. The way I would update it is, this is already 1, 1, taken and taken, and we actually take the branch, right? So the values stay at 1, 1. LHR over here used to be 1, 1, stay at 1, 1 because we are taking the branch. The next branch is now branch 2. So we now look at LHR2. You look at this 1, 1. So you're going to start looking at here and 1, 1 right here. So what's my prediction? is going to be taken, right? How about the third one? Taken again, right? And we don't have to modify anything because we are guessing correctly. It's already as strongly taken, so nothing so far. And it's going to be how many more takens? How many more takens until I predict something? Okay, quite a lot actually. We are done with this, we are done with this, we are done with this, right? Now we are done with this, this, and this because it's going to be taken again. Everything is taken so far and we don't have to update anything. Everything's correct, right? For this branch, taken. For this one, taken and don't have to update anything. For this first not taken that we see, what's our prediction? We predict taken still, right? And how do we update this? Which entry? We are going to update this. It's the third branch, right? So it corresponds to LHR3. It corresponds to this branch. We are not taking the branch, so we are modifying this into 1, 0. We are then erase this part into 1, 0 because we're not taking that branch. What do we predict next? It's back to the first branch, right? So we predict taken, and we are correct here. So we are not correct here. And what's the next one? We are predicting taken. It's LHR2. We predict wrong, so this has to change, and this has to change. Both of them change to 1, 0. We predict correctly here again because it's the loop branch. We don't have to modify anything. Over here, you predict taken, right? Because the second pattern is over here 1, 0. You look at 1, 0, here's 1, 1, right? So it's going to predict taken, and when we predict it wrong, so we're gonna erase this into 1, 0, modify this into 0, 0. This one again, predict not taken. I mean predict taken, but in reality not taken. We change this to both of them are 1, 0. This is going to be 0, 0. This is wrong, right? So we are going to change this part to 1, 0. This is also wrong because we predict taken. So that's become 1, 0. Oops, I forgot one branch. So that need to go to this first. Is at 0, 0, 0, 0, 1, 1. We're going to predict taken and we predict wrong. So we are going to erase this into 1, 0. So that's the final state of our my table, and that's all the prediction because we initialize everything to our 1. So we're gonna strongly always predicting takens. Eventually, if you keep this loop for longer, if you keep I in the loop to be instead of 5 to 50, this value would get modified to the point that each of these LHR is really good at predicting the outcome of each local branch. So you see some example when you go to the second worksheet here with the second piece of code. Any question about the two version of the two-level predictor before we move on to the next topic? And I guarantee you some of these would go into the exam. So how would it perform well again? Basically, you are trying to learn from the history, and the way you write a program, you don't end the loop at 5, right? You are going to have a loop that go to 100 or 1000 iteration. With that, the branches you're taking, at some point, everything in the table would be learned toward that block of code. So it would adapt, and finally, Finally, it doesn't rely on your initial value. The initial value becomes the learned value from the history, and it will perform well. So these particular design gets about, I think, 97% accuracy for the, I think, from the paper. That's, I think it's 96 to 97%. All right, so what about the other predictor, right? So you can design multiple types of predictor, and actually there are multiple proposals. These part I'm not going to go on your exam. I just want to tell you, okay, from this kind of like textbook branch predictor. When you say the loop ends at 100, doesn't it? Depends, right? Depends on what else is inside the loop. Basically, once you have a program running, the predictor will adapt to the program you run. So from the initial condition, the initial value, it would slowly adapt based on the history that it sees. So it will learn and it will get better and better and better. All right, so for the example of the other type of predictor, as I said, not going through the exam. It's only a few slides. I just want to tell you, okay, what else can we do? So you can add more information to global predictor by, for example, it is called gshare. Basically, you add the PC, the program counter, and then you XOR the GHR and the PC, and here's the design. Basically, you have the XOR. That's the only difference between the gshare predictor and the global history, the global branch predictor. So that's one idea. Another idea is, well, you have the global version and you have the local version. Why don't we have a tournament where you look at both predictors and pick the better one, right? So this is another idea proposed in 1999. Basically, as you can see, the logic behind branch predictor gets more and more complicated. And then I'm going to talk about the perceptron branch predictor, which is 2001 actually. Somehow I thought this is 2004. This is the one that I told you that go into the Samsung mobile phone. It actually got the most influential paper award from HPCA. HPCA is one of the top conference in architecture. So basically, this idea, the author proposed that, hey, we can learn the direction, right? And we have been trying using the table. So there are ideas about perceptrons in machine learning, and why can't we just learn the correlation between each individual branch, which is the program counter value, as well as the direction of the branch, right? And you assign the weights to all those correlations. And then you basically, this becomes like a supervised learning in branch predictor. You use a small perceptrons to train the network based on the program you're running. After a while, it would be fully trained and perform well. There's also still attempt to kind of like integrate machine learning into branch predictor using more complex learning method. One of the key issues here is machine learning requires quite a lot of complex hardware. So how do you actually integrate that is another matter. How do you actually make the hardware cheap enough? All right. So before we go into other way to handle branches, let's take a quick break. We'll meet in 10 minutes. Is that okay? All right, so let's take a quick break. We'll meet at 10:20. And I'm gonna cover what are the other things that people do, such as what does the GPU do or what does the ARM processor do to handle branches. All right, so we'll meet in 10 minutes. All right, so there was a question about reopening in class exercise 6. Sorry, it's not in my intention to close it. I'm gonna reopen that. Wait, in class 6 is already open. Do you mean in class 5? Oh, it's already open. Basically, you can submit until December 4th, and I'm not going to take any penalty on that. Basically, the in-class exercise for you to exercise, you just need to submit eventually. And it should already been set up to be available until December 4th, I think. What? Okay, let me check. Oh yeah, I need to open up this actual submission. My bad. You can submit now. Sorry, Canvas by default, it doesn't let me. By default, it was set to every assignment has no submission. I don't know who designed that. But that's a really odd design decision. So whenever I create the assignment, I need to always remember to click on that and allow submission. All right, so I hope everyone's back. Let's continue on to other way to handle branch. The first one is what you might have seen from the assignment handout. This is delay branching, or sometimes we call this the branch delay slot. The idea is when you have a branch instruction, right? When you have a branch instruction, one thing you can do is if you have a future instruction that's not dependent on the branch, this can be done through the compiler. Basically, the compiler would look at your code and it will know that, okay, these are the instructions you definitely have to run regardless of the outcome of your branch. You then execute and fill the future instruction that must be executed into the pipeline. How do we detect this? Basically, this instruction has to be independent of the branch. For unconditional branch, these are easy to fill in because you know that you have to jump to the target anyway. So you go to the target direction and then get the instruction. For conditional branch, that looks something like this. Right, so these are unconditional. These are conditional branch. You can do if or else, right? And later on, the code merge. These are harder to fill in because you don't know what exactly when the codes merge. As I said, the compiler has that information, so you can still fill in the branch using the compiler. The compiler will see that, okay, the code branch here and it will merge here. Based on the code merge, hopefully you can identify some independent instruction to fill in those slots. And here are some example, right? So let's say you have unconditional branch, so you jump to target. Over here, this is a branch, right, instruction, and this, let's say add, subtract, right? So what you have here is going to become something like this: branch, add, and then subtract. You branch, you know that you're going to have to do an add anyway, so you run it right away, and the outcome of the branch over here would jump here. So you update the PC right there. For the one that has if else, right? The one that actually branch out based on the condition. So let's say this is branch, this is add 1, add 2, subtract 1, subtract 2, and followed by add number 3, add number 4. What your code would look like is something like this. Branch followed by add number 3, because you know that whatever path you're taking, you're running the add number 3, and then add number 4. In this case, it means the delay slot is 2 instructions, so you need to fill in the 2 instruction after yourself. If the delay slot is only 1 instruction, then you do add 3, and then over here you have add 1, add 2, subtract 1, subtract 2, and then add 4. And this is where the code merge. This is branch to target. Oops. Branch to target. And here is your target. Basically, if branch condition is true, you go to target, which means you can do subtract 1 and subtract 2, followed by add 3 and add 4. Branch delay slot, move this add 3 ahead of time, so that the bubble that comes from your branch prediction logic, you don't have to do branch prediction logic right now. You just say, okay, I have to do add 3 anyway. I'm gonna move add 3 right there. I'm gonna start putting branch in the pipeline, followed by putting add 3 in the pipeline. Once the next instruction comes in, you know the outcome of the branch. So if you go to target, you're gonna do subtract 1, subtract 2, and then add 4. Otherwise, you're gonna do add 1, add 2, and then add 4. Any questions here? And you can be more fancy. Basically, if branch fall through, if branch fall through means that we are not really going to the next target. If you have instruction A, B, branch X, followed by instruction D and E, right? Sometimes the delay slot, if you cannot find anything to fill in, you put in no op, means that I'm gonna stall. No op means no operation. So with the delay slot, branch X followed by no op, because in the future, I can't find any independent instruction. The more fancy version of delay slot is over here, you can insert, right? Insert branch, you can insert instruction A into the delay slot, and you can, if this fall through, you move A to here and squash it. Basically, you squash the future instruction that that you don't have to run. Basically, if you take a branch, you do these steps. If you don't take a branch, you squash this. You follow by A, B, D, E. Another way is you can do something else. This do something else is actually one of the modern processors that use this option is the GPU. One technique is called fine-grained multithreading. And what is fine-grained multithreading? Basically, if you heard about multithreading, and we will go into more detail about the GPU and how it works. Basically, you're going to maintain multiple threads. And again, I'm going to talk about what is threading, right? And how do we maintain hardware threads, but in regard to branch. Whenever you see a branch, you run a different thread. You run a totally different program or different part of code that are independent of the branch. This is done beforehand. When you program the code itself, you program it this way, such that you have a lot of independent threads that the hardware can pick. Okay, this cycle I'm going to run this thread. This cycle I'm going to run this thread. They all have to be independent. In the GPU, for example, you're going to have a really low single thread performance. One thing NVIDIA never tell you is if the program is not GPU friendly, your program would suck. They will suffer so much that you rather run it on the CPU. It's going to be super, 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 super slow, right? And then you have to basically you need extra logic to keep the thread context. We'll talk about this in detail when we talk about the GPU and multi-threading. And then you also need enough thread to fill in the pipeline, right? And this technique can actually tolerate both control and data dependency, right? I'm going to show you an animation in the next slide, but the idea is every time you go into the next stage of the pipeline, you feed in a totally different thread. So no two instructions from the same thread are ever in the pipeline together. This is proposed actually way back in the 1960s. One of the machines called CDC 6600, parallel operation and control data 6600 actually utilized this idea. Another paper is another supercomputer, Daniel called HEP, also proposed this multiple instruction, multiple data computer, similar to how the GPU works nowadays. That's in 1978. And here are the example, right? So in the GPU, you have multiple core. Each of these boxes are threads. They are grouped into a unit called warp. And again, when we go full blown into the GPU lecture, this slide, I'm going to explain it again. But the key idea is this box are the threads. Every single cycle, right? If you look at the time unit, you actually pick one of this unit, one of this warp, to feed them in the pipeline. The entire group of threads get forward to the fetch, decode, execute, memory, and write back. Let's say warp D is in the fetch right now. The next cycle, you are putting the next warp C, into the fetch unit. Warp D move from fetch to decode. This way, if warp D has dependency whatsoever, the next instruction in warp D would happen once the warp D get out of the pipeline. So you're gonna rotate between each of these warp. And let's say warp A run into a branch or a load instruction that go to the memory, you're gonna still have warp B, C, and D to rotate into and actually execute from. Right? So the GPU core becomes active. The only case that GPU core become inactive is when all of them run into something long, such as going to the memory or branch. Then you are blocking the execution and you stall until some of them becomes available and you can proceed again, right? So these are the technique called fine-grained multi-threading, and this can be used to tolerate some of the latency of branches. So you don't have to pay the penalty. Over here, you don't even predict. Instead of predicting, I'm going to run something different. So that's the solution of do something else. The next technique, this is used in ARM processor and a lot of embedded processor, things like IoT. They got rid of control flow. The technique is called predicated execution. The idea is to convert control dependency into data dependency. So in ARM ISA, for example, you have this condition register. Overflow, negative, 0, and I forgot what's the other one. Basically, if the previous subtract instruction result in a negative value, the negative bit becomes 1. The negative bits become 1. Then you can have the add that depends on the previous instruction, add only if the negative bit is set. So you basically perform an add only when the negative bits that I see earlier is the value of 1. This is how you can do branching. Basically, instead of branching, like if else, you have the add instruction that depends on the previous outcome of subtract, XOR, or basically any previous instruction. And because it's a previous non-branch instruction, your branch condition becomes data dependency. It depends on the outcome of the previous compute instruction. This means that if you have a block like this, if, right, else, and you merge it back, right, this predicated execution convert into a straight line block of code. This is the if part, this is the else part, right? And if you want to do in the whatever is in the if, this thing get squashed. You don't run whatever is in the else part. You just go run the if and then skip to the future. And that's it. That's what the idea of predicated execution as you can see here. So let's say you have add and it's a subtract, right? Over here, add, if, subtract, yield, negative value. Multiply, if, subtract, yield, positive value. So over here, where you run this is basically add, subtract, and then add, or add, subtract, and then multiply, get cancel, right? Then this, in this case, the add get cancel, and you multiply. Or if the subtract is resulting in 0, then over here it's going to go into the positive value case, which is in this one. So you can implement if-else using predicated execution. It is common in ARM processor. Basically, this actually makes your code more compact. It get rid of the hard to predict branch, and this allows the compiler to do a lot of work. This allows the compiler to create this large basic block. So if you took the OPL class from last semester, I kind of talk about the basic block a little bit toward the end when I mentioned about the compiler topics. But basically, this allows the compiler to optimize the heck out of your program because multiple if-else convert into large straight line code. When you have a large straight line code, there are a lot of optimization you can do with compiler. The downside, if branches are easy to predict, you're going to do a lot of useless work. You are going to do a lot of checking, right? And this requires additional hardware support, which means that you need to build this logic to check in the actual chip. All right, so before we leave today, as I said in part exercise 7, there are the second example that I skipped, right? So you will do that for the global predictor and the local predictor. The way you do it is similar to what we discussed in class. And then let's assume, initial value of the GHR, LHR, and then the PHT are all 0. Assume everything in the table are starting with 0. There'll be a makeup class on Friday at 2 to 4. There'll be a 1-hour lecture and 1-hour discussion on Discord. Mostly these will be the Q&A in class assignments and the assignment we covered so far. I will definitely record the session and I'm gonna put it on YouTube because I'm aware that not everyone can make it to that particular slot. This is a makeup class for that first Monday. That was the holiday, if you remember. Basically, it's a makeup class for that particular Monday. Any comments about this format? Basically, it'll be 1-hour lecture. I'm gonna kind of going through potentially things that would go into your midterm. So I'm looking at 2 dates. either October 14th or October 19th. Which one do you prefer? That's only right now 1, 2, 3, 4, 5, 6, 6 of you. So I think we can do a vote. Let me add a vote. How do I add a vote? Let's see.